Hello, everybody. Good morning and welcome to class 36, the last class of Physics 131 this semester. Of course, there's Physics 132, which will start up in January. Same kind of thing, same book, just continuing on with at Kina. Different professor, though. You'll be with Professor Seelfen, very good friend of mine, fantastic teacher, who's taught me a lot, actually, about teaching. She'll be taking over. Right now, she's your practicals coordinator. Just to give you the idea here of, take a look at my screen too. We've got course review, a liquid nitrogen demonstration. There's a final bonus team up quiz, which is hopefully you guys can see that. Just check my chat. There's also, I put there a little news article yesterday on the CBC. Health Canada approves the Pfizer BioNTech COVID-19 vaccine. So I kind of feel like this is, maybe this is all going to end next year at some point. We'll all get vaccinated, be immune. So there's going to be, I think what I want to do is talk about the final assessment and maybe do a little practice. You're going to be able to find it on Quarkus under a new module called Final Assessment, which is there now. The format is a 30-minute multiple choice test followed by a 10-minute break and then a 35-minute 2-question written answer assignment to be submitted on CrowdMark. And somebody asked me last time how they're weighted. Half of your final assessment mark will come from the multiple choice, those 10 questions, and the other half will come from the written answer part, which is marked out as 16, but they'll be scaled so that they'll both be worth the same amount. And the timing goes like that, starts at 7:10 p.m. on Thursday, December 17th. So it's a week from today. I think that's it. So what I've done is I've posted the rubric for these 5 possible chapters, so you can take a look at that right now. Actually, on the Quarkus. Some stuff going on in the chat window, just people chatting about what's going on with the vaccine and stuff and allergic reactions. It's going to be, I think maybe 2020 was like the year of this virus, and 2021 is going to be the year of the vaccine, trying to figure out how we're going to get the vaccine and which vaccine and all that stuff. And I heard that Ontario is going to be issuing like vaccination cards, to show that to prove like if your photo ID, so that I guess you can get into stores and stuff like that. It's going to be a weird year for sure. Yeah, Carol Zhao was asking if our final grade lands on a 0.5 or above, will it be bumped up to the next percentage? Yeah, I can only submit an integer to the grades on Acorn. So like if you got 89.5, then that would be rounded up to a 90, for example. And yeah, that's the same for all courses, I think. Let me stop the share, because what I want to do is actually move things around a little bit and show you right now the liquid nitrogen demonstration. I'm a little anxious to do that. So I'm going to take my camera and point it over here. I'm also, carrying my laptop, so I actually still have the chat window open here, and I can see what you guys can see. So that's good. And I can put on my participants. So actually, you can see what's going on here is I've got some, I've got a train here. I've got some liquid nitrogen. When you're working with liquid nitrogen, it's good to put on Hello, everybody. Can you hear me? I'm back. Sorry, everybody. I think maybe when I moved it, I must have knocked out my internet connection a little bit. So what I want to show you, I can see you guys in the chat window still up there. So you can alert me if anything weird is going on. Yep. Hi, hi, hi. So what I've got is, I'll put on my gloves here, is I've got a dewar full of liquid nitrogen, which is Pius has produced for me. So what it is it's air, which is cooled down to 77 degrees above absolute zero, which is the boiling point of nitrogen. So it looks like water, but it's boiling. It's nitrogen that's boiling because it's right at its own boiling temperature. And then, so that's it. It's kind of just cold stuff. You can pour it out if you want it. You don't want to drink it. It's very, very cold. You don't want to touch it because you can get burned, and you don't want to touch anything that's touching it. And what I've gotten here actually are these little pellets. I was going to also pour some in here as well. It's a little tray. This is a pellet of what's called yttrium barium cupric oxide. And if you put it on a magnet, it'll actually float there. So what I can do is try to put the camera down so you can sort of see what's going on there. See a little floating magnet going along. Whoop. Don't be shy. Dip Cheetos in it. You can do that. Yeah, so this is just what it does. This is called the Meissner effect, which is that it becomes magnetic when it's superconducting. So this thing will levitate until it starts to warm up and then it falls. You have to cool it so that it becomes a superconductor below its critical temperature, which is about 100 degrees Kelvin. So when it gets down to 77, it's cold enough to be superconducting, expelling all magnetic fields around it, and then it kind of levitates on its own little magnet there. I can also put it on a magnet. Another strong magnet there, which I can put it in here again. It keeps on warming up. I think I might have a better, put that there. One thing at a time here. Dip it in. And put it on here. And now you can kind of see how it sticks there. And I can kind of, that fell off. I push it on a little bit and it sort of sticks and doesn't want to fall off. Whoa. I don't have any solid nitrogen. Okay, I want to see it sort of more up close. So that's kind of how it works there. And there's nothing up my sleeve. I think I have another one actually where it's doesn't fall quite as fast. Use the tongs to get that out here. This one. This has got a yttrium barium cupric oxide superconductor sitting inside it, and but it's also encased in sort of a foamy thing. So that one, again, I think you can even sort of turn it upside down. And so it's actually, well, it's draining the nitrogen in there, but it's pulling as well as pushing. It's locking the magnetic field in at that particular distance. So that's kind of a cool thing. And then the other thing that we can do, so I'll just leave that there and see how long it stays there. When you can see, maybe I can show you that there's no like tricks up my sleeve or something like that. It's really just actually levitating there. It's kind of a cool thing. Cool, get it? Okay. So that's that. The other thing I can do is I have a rose. So does anyone here want me to dip the rose in the liquid nitrogen? Yes, okay, Lauren. All right, so I'm gonna do it. Not a nice thing to do to a rose. We might as well try it, see what happens here. Oh, it's really boiling as it, because the rose is at room temperature, obviously, which is boiling off a lot of the nitrogen. Let's see what it looks like when we pull it out of there. So this is a very cold rose now. Oh, see it's already kind of flaking away and becoming brittle. And of course, I'm making a big mess with that table there. So we can try that. Sort of smashes. Okay. I think that's it. Made a little bit of a mess. Sorry about that, Pius. I'm sure you're in there kind of going, what is he doing? We'll clean that up a little bit after. So now I'm going to move my computer back to where I like it. And hopefully this doesn't cut out. Carefully. Oopsie. Okay, so that was our demo for today. Am I still in here? I don't know what all the F is about. Okay, good. Oh, for the rows. Okay, you guys are having fun on the chat window here. I have no idea why there's an F. You guys are going to have to explain it to me. Okay, I'm going to share my screen again. I think it might be a good idea to go over a couple of questions here. Make sure my chat is still up. Oh, to pay respects. I did not know that. Never played Call of Duty, so maybe I don't know what that's all about. You guys are going to have to educate me. Okay. Good to know. And I'm back. You guys can hear me. Maybe we should get a little more serious. Let's actually, Ezra, did you have a question or comment?
Well, I had a question about like the demonstration of like
Yes.
the magnets. What would the force diagram look like since there's no normal force on?
Yeah, well, it's the magnetic force, isn't it? So instead of the normal force, it's the magnetic force. And so what is happening is that the superconductor has become a magnet, basically, and so there's a force between it and the permanent room temperature permanent magnets underneath it. And if it gets a little closer, then that's a repelling force which pushes it. If it gets a little farther, it becomes an attractive force which attracts it. And it's just due to those magnetic fields. But you'll be learning more about that in Physics 132.
Oh, okay. Thanks, sir.
Here. And Human, did you want to unmute?
Harlow, can you hear me?
I can, yeah, hi.
So I am doing the mirror final assessment, and
Yes.
I am confused to whether that is on December 17th or 18th.
18th.
18th. Oh, yeah.
It's just 12 hours later.
Yeah, in the Kirkus is 17th, so I was confused.
Yeah,
Yeah.
no, it'll be after, yeah. So it was a little after. So it'll be 12 hours after in this case.
18th, okay. Thank you.
Okay, sure. Anybody else is good? Yeah, I was wondering if I should go through these some of these rubrics. So yeah, these are the 5 different rubrics. We can actually go through a couple of questions. Why don't we just do that? Again, I think it's kind of serious business when you guys are actually have a final assessment coming up. You could read through all this, but it's already on your Quarkus, right? So why don't we just do an actual problem with it? Let's suppose, and this is like the flying pig problem, that you have an airplane attached to the end of a 46 centimeter string. So I'll just draw the airplane kind of like this. Airplane. It's a toy airplane, and it's attached to a string. This is L is equal to 0.46 meters. And this angle theta right here is equal to 25 degrees as it goes around in a horizontal circle. So just like that flying pig, it goes around in the circle with some radius r. I think that this will also be theta, so that r is going to be L times cos theta, which I think turns out to be 0.417 meters. You're asked to find T is the period, not the tension, but the period. And this is like a circular path. And it's something that you may have been familiar with from your practicals. The system here is the airplane. We're not doing a filter today, although I guess I could try one. Somebody mentioned we need a filter here. This is going to be my choice today. What's the good one? Magic Horn, I think. I'm not going to include the Earth because what I'm doing here, I'm not going to use energy. I'm going to do a force diagram. It's a good question. So here, I'm just going to call it the force of the string on the airplane, not T, because T is the period, so I don't want to get confused. And this will call the force of gravity of the Earth on the airplane that's acting down. And right here is your theta, okay? So I'm going to define R towards the center of circular motion and Y to be up. I'm going to assume constant speed. V is equal to 2 pi R divided by T. And A sub R is equal to V squared over R, okay? So we can say that the sum of the forces in the Y direction is equal to 0, and that's going to be the F sine theta minus mg. So what that means is that F is mg over sine theta is the tension in the string. And then we can say that A sub R, which is the V squared over R, you can use Newton's second law and say that it's the sum of all the R forces divided by the mass. So it's going to be F cos theta is the only R component of the force divided by the mass, which is going to be, I think, G cos theta divided by sine theta, because the m's will cancel there. So what you get is V is equal to the square root of R times G cos theta divided by sine theta. So V, I think I'll just solve V numerically and then find the T. It's going to be the square root of 0.417 times 9.8 times the cosine of 25 degrees divided by the sine of 25 degrees. I plugged all that into my calculator and I got 2.96 meters per second. That's not what we're asked for. We're asked for the period. That's V. So T is equal to 2 pi R divided by V. So it's 2 times pi times, again, 0.417 divided by 2.96. And I got T is equal to 0.88 seconds. Okay, similar to the flying pig, I guess. Flying pig practical. And Ethan's right. So if you're going to do a system including the Earth, that's when you're going to use MGH for the energies. Mia, did you want to ask a question?
Hi, can you hear me?
Yes, I can.
All right, first of all, I just wanted to say thank you so much for the amazing semester. And I just had a question about the written questions. Will there be 2 units combined in a question, or will they be specifically separate units?
It'll say, just like this one, it'll say the actual chapter for each question. So it's random which of these 5 chapters, 5 or 6, or I think it's 9 or 10 or 11, but it'll be one of those 5 chapters only.
Okay, perfect. Thank you so much.
Sure. Should we do another one? We got time here. And yeah, Shreya, good question. Will the multiple choice of the final be like previous midterms where we won't be able to go back on the previous questions after seeing the next question? Yes, that's correct. It'll be just like one of those midterms. That's the way I feel I have to run these. Chapter 6 was impulse and linear momentum. just to show you an example of what this looks like, you want to draw some sort of momentum bar chart. So if you have a 0.2 kilogram bullet traveling horizontally, what you want to do in your sketch is do your initial situation, which is that here's the bullet going along. We can call it the bullet initial, I guess. And it's actually given 250 meters per second. And then what you've got is a big block, which is the like wooden block, I guess, for wood, is equal to 0 initial. And then you can draw the final situation, which is that the bullet is kind of embedded, means it's stuck in. This is an inelastic collision. Inelastic collision. And you want the VB wood final is equal to question mark. So I'm going to assume no friction. What this means is that there's no external impulse on the system. The system is equal to the bullet plus the wood. So if I do P of the bullet initial in the X direction, I'm also going to set plus X to be towards the right there, plus P of the wood initial in the X direction, plus the impulse in the X direction is equal to the P of the bullet and the wood final. So these two are 0. So what you've just got is that the mass of the bullet times the V bullet initial plus 0 is equal to the mass of the bullet plus the mass of the wood times the V of the bullet final. Bullet and wood final, sorry. So V bullet and wood final is equal to the mass of the bullet divided by mass of the bullet plus the mass of the wood times V bullet initial. So it is equal to 0.2 divided by 0.02, 02 plus 1.0 times 250 is equal to 4.9 meters per second. Okay, this is a lot less than the speed of the bullet. Since the wood is a lot heavier. So many things coming through in the chat here. Maybe Ali, did you want to unmute?
Yeah, sure. Can you hear me?
Yeah, I can, yeah.
I just had a question about where we define the system, because in the lists you provided, I think most of them define the system in phase, but when in these two examples, we've done it in simplifying that.
Yeah, you're right. It should have been in the sketch and translate.
That's it. Thank you.
Okay. So listen, do you guys want to do, since we're kind of, it's right around the halfway point here, let's do the team up while we're all here, 11:34. I've got a couple more examples I was thinking I might do, but let's do team up time. There's something that you should be able to see right now on your Quarkus called Team Up Quiz Bonus Course Review. Your pod team shares the mark. So right now what I want you to do is open up your Microsoft Teams and somebody place a video call to the members of your pod chat so you can see each other, hear each other, and chat about this team up. First step is to decide who will be the team up driver. And then everyone logs into Quarkus, and you know the routine. Drivers have to start a new session and share the session ID with everyone else in your Microsoft Teams chat. Non-drivers, once you get that, you join that session so that everyone in your little room there, in your call, arrives in the team up. And then you can start going through the questions. There are 4 questions today, which I'll go over in about 15 minutes. Let me put on my timer for 15 minutes here. I'm going to put myself on mute. We'll have another 10 minutes at the end to discuss these things. And I'm also going to open up the, oh dear. Hit a button here. I'm going to open up the help center, which I haven't done yet, and see if there's anybody who wants to join that way. Okay. Everybody, about half a minute or so. Go over some of these. These are pretty difficult questions. Okay. We go over these 4 questions, so you're not left wondering. Annie makes a good question there. Should we keep our calculators in radian or degree for the final? I think the safest thing is to keep it in degree mode, but you have to be careful. You might have to have it be able to switch it to radians mode. You almost always use degrees, though, I think, in this course. It's just this way of business. You want to go over question 1? This is the steel square frame. People didn't do so well on this on midterm 5, so I thought I'd go over it a little. 1 meter by 1 meter in size, and it weighs a total of 4 kilograms, can be thought of as 4 connected steel bars. So what I think is, for the sides one, side, just use that it's mass times r squared, where this is the distance right here, right? Distance from the rotation axis. And r is equal to 0.5. So it's equal to 1 kilogram times 0.5 squared. So it's 0.25. And then the top, this is, you have to actually go to the to that table, and it's 1/12, I think, of m times l squared, where l is the length of the thing. When you've got a bar that's rotated around the center, it's 1/12. Yeah, Faison asked a good question. The rotational stuff is in radians per second and stuff, but you don't often type cos or sine for it. So I guess that's why you don't really need to switch your calculator to that. So it's going to be equal to 1/12 of 1 kilogram times 1 meter squared. Anyway, it's a 12th. It's 0.0833 repeating. And so the I total, there's 2 of the sides. So it's 0.25 plus 0.25 plus 0.083 plus 0.083 for all the 4 sides. And when I added it all up, I got 0.67 kilograms meters squared. So I guess that rounds to B. And Joshua, that's a really good point for questions like this. If it's on the exam, I will try to remember to give you that rotational inertia equation. But it might be good to know where, put a post-it note on it in case I forget. And so, and Dima, good question. So for the sides, what I'm doing there is I'm just using all the mass. When all the mass is at the same distance from the rotation axis, it's just mr squared, and there's no factor out in front. You only use these factors, like a 12th, if you've got a shape which is rotating around, so that different parts of the shape are at different distances from the rotation axis. And that's top in the end, sorry, I bottom, same. They're the same, right? Should we go over, a couple questions on the chat. Jerry?
Yeah, hello, Prof. Yeah, since midterm, I have this question, but I never had a chance to ask. For those kind of rotational inertia, why is it that for the mass on the side, don't use a formula?
Because all the mass is the same distance from the rotation axis. It's like a point, right?
Okay, so whenever there's like a point,
every point on this object is at the same distance from the rotation axis, r. So it's just the sum of all these masses times r.
So we treat them like a hoop.
Yeah, like a hoop, yeah. Because that's the same with the hoop. Hoop is the same thing. Every point on a hoop is the same distance from the rotation axis.
Oh, okay. I see. Thank you, sir.
Yeah, you're welcome. And Ethan?
So the way I did this problem is that I just use 1/12 ml square and then put 4 kg as the mass. Why did that not work? And 1 meter as the L.
Well, because you've also got the edges, I think, right?
Oh, but what doesn't like 1/12 account for the entire rectangle? At least that's...
Well, if it was filled in, yeah, it would be. If it was a solid rectangle, then yeah, you just use 1/12. But this is a steel frame, so so for the outer edges here, all the mass is concentrated at a distance of 0.5 meters from the center. Whereas if you had what you're suggesting, like a filled-in rectangle, then it would be spread all over those different distances.
So in the context of this question, what does the 1/12 ml square like represent? Like the top
Yeah, just the top and the bottom only.
Can you like explain why that is?
Because those are the objects that have mass like at different distances from the rotation axis, right?
Yeah.
Anytime you have an object where it's got some of its mass spread out at different distances from the rotation axis, then you have to go to that table. But if it's oriented in such a way that all the mass is at the same distance from the rotation axis, then you just use mr squared. You don't need any fraction.
Oh, okay. Yeah, got it. Thank you.
Yeah, you're welcome. Question 2, stationary bike has a wheel that rotates while its axis of rotation does not move. The wheel has angular acceleration is constant. Okay. Which of the following statements is true? The magnitudes of AT and A, so basically AT is going to be R times alpha at the edge of the wheel or something is a constant. Ethan, do you want to put yourself back on mute? And AR is equal to V squared over R, where V is equal to omega times R is changing. So that's not true. Which one is right? Magnitude of the tangential acceleration is changing with time. That's not true. Magnitude of the tangential, is constant, but the magnitude of the radial acceleration is changing with time. So as V increases, then that will increase. If that makes sense. Question 3, Earth's orbit around the sun has the same major axis of, so this was something we did a little while ago. This is Kepler's law. You remember that one? Which is Kepler's third law, which is that T squared divided by R cubed equals K. This is equation 5.5. from page, I think it's page 137. So what you can do, it's the same constant for any planets. So T1 squared over R1 cubed is going to be equal to T2 squared over R2 cubed. And you can rearrange that and get that R2 is equal to R1 times, I guess, the cube root of T2 over T1 squared. So it's going to be the 1.5 times 10 to the 8 times the cube root. So you have to find cube root on your calculator of 1.6 divided by 3.2, which is the half squared. So you'd square a half, cube root it. What I got was 0.95 times 10 to the 8 meters. Interesting. And I'll save these and put them up on the screen. And then the last one was the thing that messed you guys up way back in midterm 1. You walk half the distance to school. So here's your, let's switch to blue, I guess. Or here's your D over 2, and your V1 is equal to 1.0 meters per second. You go that far. And then here's your D over 2, and you go V2 is 4 meters per second. So what you're going to do here is V average is just equal to D divided by T1 plus T2. But the problem is you don't know T1 and T2. So what you're going to do is say that V1 is equal to D over 2 divided by T1. You can solve that out. So what that means is that T1 is equal to D over 2 times V1. And then V2 is equal to D over 2 divided by T2. So that means that T2 is equal to D over 2V2, right? Anyway, you guys can do it, right? So V average is equal to D divided by all this stuff, D over 2V1 plus D over 2V2. So the D's all cancel at this point. You can divide top and bottom by D. You'll get that V average is equal to 1 divided by 1 over 2 times 1 plus 1 over 2 times 4. It's equal to 1 over like a half, 0.5, plus an eighth, which is 0.125, right? I got 1.6. That should have been pretty simple for you guys. It's just an old style kinematics question. You know what? I'm going to stay on this call for a half hour just to chat with anyone who wants to hang around. But I think that's pretty much a wrap for me. It's been a weird one, hasn't it? Single strangest class. You guys were my first Zoom call for teaching. And so I appreciate your patience with me for the whole semester as, you know, I figured this out. Somebody told me about Snapchat, so I put it on my phone. No idea how it works. You know, I'm so out of it. Maybe I'm just a little old for this. I am almost 49 years old, so that's probably the reason. Don't forget to do course evaluations. Please email me if you've got any questions. You can either use, that's my actual personal email address, or you can email the Physics 131 fall that goes through April, and then she can deal with a lot of stuff as well. Keep in touch. And maybe when this whole COVID's over and we all have our little vaccination cards or whatever, we can get together in my office and you can come by and say hi. So it's it's been great. I'm going to turn off the record and then see if anyone has some chat. So bye, everybody. Bye, bye, bye. Have a great break. And hope to see you around.